Maybe Giorgio, while waiting,
Yeah,
you can provide information on the lunch.
Yes. Lunch will be at 1 o'clock, immediately after the class presentation. But we have to go where we were yesterday. So it's next building, you know, where the head of the department of engineering has his office. So we have to go to residential engineering architect. So but we will go together, and we will have a lunch break from 1 o'clock to 2:30, and then we will have the last presentation, which will complete actually this overview on brine valorization. And then, Andrea, I think we will have some small break, 1 hour break from 15 to 16, from 3 to 4 o'clock in the afternoon. But at 4 o'clock, we'll then go to visit, to make the lab tour, and actually will be an occasion, an opportunity just to see what we are doing here in Okay. So, brine treatment process for raw materials. We're already within the topic. We've already seen quite a few concepts already explained. So we all know that brine composition can be, of course, different from site to site, but definitely we have major components and minor components. But this is very interesting because, of course, in seawater there is a lot of compounds, and of course that makes very interesting the possibility to recover either major ions or minor ions. The technology, there is really a very large variety of technologies. So there are, let's say, membrane-based technologies or non-membrane-based technologies. For the thermal-based technologies, you see here just a few of this technology that are relevant for our presentation. So wind-aided intensified evaporation, salinity gradient solar pump, theoretic freeze crystallization, and membrane distillation, membrane crystallization. Of course, I won't repeat for the case of the technologies that have already been discussed in the previous presentation. Maybe we can just mention wind-aided intensified evaporation. So this is a very simple technology somehow. I mean, you have these vertical surfaces, and over these surfaces, of course, you make flow, you make the brine to flow, and basically with this proper scheme, you make the evaporation process going on, and at the very end, of course, you succeed in, of course, concentrating brine and producing salt. The main point is that, of course, you get low quality salt, so non-selective crystallization. You have, of course, a significant maintenance, so labor intensive, and large amount of waste solids to be disposed. The advantage is extremely low energy consumption, easy operation. It's very simple technology, not largely implemented. Interestingly, just to mention the eutectic freeze crystallization, and this is based on the principle that each saline solution has a so-called eutectic point, so a particular point in the phase diagram where there is an equilibrium between ice, salt, and the specific concentration solution. So if you operate correctly by cooling a saline solution until you reach the eutectic point, you can get ice and salt. And what is interesting with this technology potentially is the energy consumption. So theoretically, you should have an advantage of lower energy consumption. But of course, the feasibility of the recovery is not at all, I mean, it's not really very practical. So there are difficulty of dealing with solid liquid separation. And of course, higher cost of producing cooling rather than heating. We all know that refrigeration is not is costly compared to heating. Membrane distillation, we've already received, presentation by Guillermo, so I won't mention really anything, but I can say that of course we can go up to crystals. We can actually have what we call membrane crystallization, membrane distillation, membrane crystallization, and in this case, of course, we would reach production of salts. Well, of course. These are the main advantages and disadvantages, which have already been described. Another interesting thing is salinity gradient solar ponds. This can be used in combination in order to, let's say, have a source of thermal energy. And of course, this source of thermal energy can be used as a thermal storage or just for processes that can even to power a desalination plant. So if we look at the energy consumption, well, there are data. These error bars, of course, they just say a lot about the different data that you can come across in literature. So I believe that, for example, in this case, for authentic freeze crystallization, there is a lot to discuss depending on the order and the results that are collected, as well as for the case of membrane distillation. But I think you presented much more detailed data on this point. For technology readiness levels, well, this could be also something questionable again. So maybe for the case of membrane distillation, maybe we are well above 5. I guess we could be, and possibly for eutectic free crystallization, of course. So I mean, there's not really big difference. But in the practical implementation, yes, there is a significant difference. Then we go to the electrobedded process. So high salinity electrodialysis, reverse electrodialysis, and electrodialysis metathesis. These technologies have already been described somehow. For sure, electrodialysis is one of the traditional technologies adopted in the desalination industry. But in this case, of course, reference is made to the case of high salinity. So the treatment of brines to produce a concentrate, of course, and diluting the other stream. Of course, disadvantages for such case of high salinity electrodialysis is the high energy consumption. We may have additional pretreatment requirements. And of course, we are not going to have a stream, with freshwater production. Of course, it's not feasible at all. But it is possible to achieve a significant high brine concentration, which may be the main purpose of use of such technology. Electrodialysis metathesis was mentioned a moment ago in the previous presentation by Angel, and of course, it's a special electrodialysis process that has a special, capability to concentrate ions in such a way that these ions will shift from a solution to another, and then you can, of course, get, specific solutions with some specific ions. And of course, you can increase concentration in a significant way. We may have, of course, among the disadvantages, high energy consumptions, but as the advantages, of course, we may have high purity of products and high current efficiency. And of course, it is less affected by scaling. Reverse electrodialysis, this is a completely different topic. It's been already mentioned that among the different possibilities, brine valorization, there is also the possibility to recover energy. Energy can be recovered, of course, through this technology, reverse electrodialysis. And I think most of you are already familiar with this technology, which is somehow reverse. It's just the opposite direction of the desalination electrodialysis process. And the main point is that still you have to consider the, let's say, economical feasibility, sustainability of the reverse electrodialysis process, because what you produce is electricity, and electricity should be on the market with a given price. And we have still the problem of low power densities and the cost of ion exchange membranes, which of course generate a problem in terms of the cost of the electrical kilowatt hour produced. But in the future, maybe we will, of course, achieve in the future better results, getting closer to, let's say, economical sustainability. Among the advantages, I would say, with reference to another technology that we will be mentioned later on, there are no moving parts and the direct conversion of electricity. We are making reference to pressure retarded osmosis, which is the other technologies that I believe was mentioned. So this is a scheme for, of course, energy consumption, depending, of course, on the different technologies. So high salinity electrodialysis or electrodialysis metathesis. Of course, for reverse electrodialysis, you don't have an electrical consumption, but a net positive production. And you see here that for the technological readiness level, still there is some way to go for the reverse electrodialysis technology. So pressure-based and convenient process, going on with this presentation. It was already mentioned, high pressure reverse osmosis, previous presentation. So nanofiltration, osmotically assisted reverse osmosis, and pressure retarded osmosis, which is a companion technologies to reverse electrodialysis technology. And then a possible combination between thermal and membrane, which is thermally driven forward osmosis, which makes use, for example, of thermolytic salts. So high pressure reverse osmosis, I mean, it has been said that, of course, we can go to treat, with higher pressures, more concentrated saline solutions, and we can operate in the range 100, 120 parts. But of course, there are significant limits to go at higher values, I mean, mechanical resistance. So it's a possibility, of course, but we have also to consider the other options for the case of high pressure reverse osmosis. Nanofiltration is one of the technology that could be very useful in order to generate a kind of, let's say, first treatment of the brine when you want to separate, for example, monovalent ions from bivalent ions. And of course, it's something in between. You see reverse osmosis and ultrafiltration, so that, let's say, energy requirement, they go and they stay in between. So among the advantages, of course, low operating pressure with respect to reverse osmosis and high bivalent ion rejection, which makes possible this separation when you treat, let's say, brines that comes from sea water. Osmotically assisted reverse osmosis, I think it's very interesting, especially for the case of brine concentration. And that has been already discussed, that it's a kind of combination between the forward osmosis and the reverse osmosis. And in this case, of course, we may say that there are some disadvantages, such as, system is more complex. You need to select the appropriate draw solution, and you have high capex. Then pressure retarded osmosis. Among the two main technologies for, let's say, energy recovery from brines. We just said a few words on reverse electrodialysis. I'm not sure whether this afternoon we will see a unit or not.
Yes,
so there will be this possibility to see a unit. But pressure retarded osmosis, of course, it's another option. Of course, you do not have a direct conversion of the, let's say, salinity gradient into electrical energy, but rather you have an increase of pressure, or let's say you have a flux, a pressurized, let's say, stream that then can go to a turbine, and then there is a mechanical transformation from pressure energy into mechanical energy, and subsequently to into electricity. Of course, this generates a chain which is more complex with respect to, let's say, the intrinsic simplicity of the reverse electrodialysis, and also different problems with respect to operation. For example, I would say that since what you transfer, the transport is mainly water that goes through the membrane, rather in the case of reverse electrodialysis, you have the transport of ions through the membranes. Of course, membrane fouling is a completely different issue in this case, rather than the case of reverse electrodialysis. Still, there are some attempts to implement this technology. European level, there have been in the past, and also I think in the Far East, there have been a few examples of application. And then we have this other combinations. You see, combined process, thermally driven forward osmosis, where basically you use a special concentrate draw solution, which makes use of thermolytic salts, for which, of course, you have to then, let's say, to manage the proper regeneration. But with this, of course, you may start with a feed and concentrate through, let's say, forward osmosis with this specific draw solution, which has, let's say, in principle, some advantages for the regeneration, I mean. Okay, so this would provide, again, a simple comparison in terms of energy consumption. So for the osmotically assisted reverse osmosis, the high pressure reverse osmosis, and the thermally driven forward osmosis. Of course, nanofiltration stays on another side, but it is intrinsically a different process. Technological readiness level. So still there is some way to go for the commercialization of many of these systems. And last but not least, this was the point I wanted to reach. All of these, let's say, variety of technologies, they then offer the possibilities to be combined together to have a proper circular processing of brines. You see, in this case, it's a very special type of brine, which is a salt work bittern, the circular mine project, the one that you will see in the lab. You will see this integrated chain that I'm going to describe very briefly. But it's very relevant even to the case of this fast track school, because actually you see from this circular diagram that you may start from seawater, and when you go, sorry, okay. You start from seawater, you go to a desalination facility, so you process seawater, and you get a concentrated brine. Now the point is this: what you do with this concentrated brine? Within the circular mine project, the idea is that the concentrated brine can go directly to a traditional salt work, so traditional evaporation pond, where you produce sea salt. After that, at the end of the cycle, what you get is a bitter that is very rich in minerals. And this is very significant for us because it makes a significant difference in terms of concentration of the minerals, of the compounds that are present in this bitter. And this makes possibly more interesting even from an economical point of view. I mean, the recovery, for example, of magnesium, which can be extracted. And in fact, this will be the case of the technology that has been implemented within the circular mine project, targeting at specific recovery of magnesium, but also lithium extraction and extraction of other trace elements, the minor elements that we have been discussing a moment ago. Let's see. So there are these three main, technologies. I'm not spending any words, Andrea, because for sure during the tour there will be time to present the different technology. So the magnesium crystal granulometry controlled reactor, the lithium membrane flow capacitive ionization, and the trace elements pH swing adsorption. So these are very specific technologies that in turn, of course, they target the recovery of magnesium, lithium, and trace elements such as strontium, rubidium, cesium, cobalt, germanium, and so on. Of course, within what you will see, because in the tour this afternoon, you will see in the laboratory that is devoted to this implementation of this integrated chain, there are, of course, other auxiliary units that are necessary. And particularly, you see there is a unit, electrodialysis with polar membranes, was mentioned a moment ago, because we have this in situ chemical production, because the circular chain is totally self-sustainable. So that doesn't require an input of chemicals from outside. So you produce what is needed for the precipitation, the reactive precipitation process. And also you have, in principle, the possibility of recovering through reverse electrodialysis electricity, because you still have, let's say, saline streams that offer this possibility at the end. Actually, you see here, at the end of the process, you still have a brine which contains significant amount of salt. Okay, so said that, I think I want to approach the very end of this presentation and the end of this morning, say that this is not the only project that we are running at the moment at the University of Palermo. So we are involved from PSA in the water mining. The water mining is a very large project that I think it will come to an end by end of this year, 2024. And within the different, very large project, some 20 million euros project run within the Horizon 2020 framework research scheme. And there are a number of case studies. This is the so-called case study 1. I believe you are also involved in case study 2. Exactly. And this is with particular, let's say, reference to the case of the island of Lampedusa, which is somewhere in between, in the heart of the Mediterranean Sea. And the idea is that of having this seawater treatment chain, which I'm not going to describe. What you see is that, again, you have a nanofiltration as a pre-treatment, which basically provide a permeate, which is rich in monovalent ions, and of course a retentate, which is rich in bivalent ions. And you start, so from seawater, to separate two streams, and one will go to the recovery of magnesium hydroxide or calcium hydroxide, and the other one will go to a multiple effect distillation unit, for the production, of course, of water, at the same time of very concentrated brine that will go eventually to an evaporation pond. And further, you can go even to, of course, use the remaining stream that comes out from this treatment chain to an electrophoresis with bipolar membranes that will generate, of course, the chemicals that are required for this treatment chain, in particular for the reactive precipitation. So this is, of course, not at all a very detailed description, but it's just to provide two different examples of what could be an integrated treatment chain for different cases. This is a small island starting directly with seawater, or the case of the circular mine. The original idea comes from what happened in Trapani, where actually there was a desalination facility, and nearby the desalination facility in Trapani, there are actually a lot of salt ponds, and so the combination of the desalination and the brine coming from the desalination facility will then be fed to, let's say, a traditional salt works, thus generating a significant increase of the production of the salt pond. So it was for the local owner of the salt works that was very beneficial, because with the same, infrastructure, they could get a significant increase of the production of the sea salt. At the same time, we could then implement all the rest of the chain. So I think it's very valuable also for, from an economical point of view, in principle, to implement this kind of technologies in the future. So I think we are still on time, Andrea. I'm not sure whether we, yes, I think we're still on time. We may end up, Pedro, for today, this morning, and of course, we may open to this. We have to go at 1 o'clock.
Yes, but you have to wait for the question.
Of course. But maybe, Pedro, we can also summarize that, of course, this has been just, let's say, an overview of state of the art, and these propositions that have been mentioned, they just try to provide what is going the future beyond the state of the art. And it's also our intention, and I think you have mentioned in the previous presentation, not me, what is the arrangement, our proposition within the salt to water project, that we are pushing also the barrier beyond state of the art.
Yes, in the salt water project, we have a lot of time and opportunities to sit down and discuss and think about the pilot we want to develop. Consider that we have here a specific attendance of candidate researchers and researchers which who have been provided with a lot of information, I guess. Some of you, some of the information was already known, others maybe not so much. So still, we have time for questions, for common
Curiosity,
of course. Regarding our pilot, of course, we will have a chance to see it. I will not take it against it right now.
No, not at all. Not at all.
There will be quite a lot of information that we take.
Yeah, definitely. It's a big, very open to very different developments, depending on the type of technology that you select, whether it is membrane or non-membrane based, whether you are targeting recovery of energy or valuable, let's say, compounds. It could be that you target the natural ions. We didn't discuss a lot about the different scale of production that comes, depending on this different level of concentration. Because, of course, when you target trace elements, of course, it's a significant challenge. I mean, the amount of ions that you can recover and the cost associated to the recovery of this ion, minor ions that are present. In some cases, it is a big challenge. But in principle, of course, I think it's very fascinating, and also could be an important options, an important resource in the future. I still remember the case a long time ago with some colleagues of mine from the chemistry department, and I remember that they were mentioning the possibility of recovering uranium. This basically was a research program run from an American institution, offering, of course, funding for this, because, of course, that is a strategic, let's say, issue, the possibilities of recovery uranium for, let's say, special application in the defense sector. So it's quite interesting in principle, looking at brine coming from desalination, because they offer a very wide variety of compounds. I would say almost all the periodical tables is there. The problem is the concentration at which each of the elements are present, and very, very challenging.
No question. It's a big opportunity for you, huh?
To ask a question and to get no answer. Okay, Andrea. So, but once again, we have just lunch break, but we have to come back at 2:30, Andrea. If I look at here in this room, okay?
Yes.
So 2:30, and now we go. Maybe we go all together, just to avoid that someone is.
Myself and Nick will stay a few minutes to check.
Okay.
And the door will be not locked. So if you have something precious, like
Oh yes,
do
not leave anything
bring it
here.
with you.
Just bring with you, or we may.